Okay, welcome Tammy and Chanel and Will and Joy and Aze, which I know that's not your name, but I'm always forget. Um, Thanks for coming, and I apologize for didn't even realize that we had this going um, on the same day and the same time as President Trump is giving his State of the Union address. But I don't know; it'll be recorded. Both will be recorded, so there you can watch both. That's for sure, if you want to. So today, the first thing I want to let you know is that um, I'm not sure. Any of you from Tahoe? Any of you live in Tahoe or in Tahoe now? So if you don't know, Tahoe has just experienced something pretty tremendous, and that is there's about 4 feet of new snow in front of my house and the whole town, and everything is closed down. So the good news is our electricity is up, so I'm actually able to give this. The college is closed. I can't get to the college, and I can't do it on the college equipment. So I apologize. I'm just sitting on my laptop. I don't have all the extra double screen technology, which you probably don't even notice, but it makes it so that I can bring things in faster and stuff. So I don't have quite the technology I usually have, so I apologize for that in advance. But either way, we're still going to do what was planned, and there is one main thing coming up. It is the final deadline is Sunday. I recommend strongly that you submit your rough draft of Project 1 by Thursday at 8 a.m. If it comes to me after that, then I won't read it, but I will answer any questions you post on the project discussion forum. So the Thursday at 8 a.m. is the absolute deadline to be able to submit your project. And what I will do for the project draft, so I can give you suggestions. What I will do is I'll give suggestions. I'll give a kind of a top 10 list is what I usually do. Sometimes more, sometimes less, but just around 10. And yeah, I got it, Tammy. But I only got it a half an hour ago. I needed to prepare for this. And so there wasn't enough time for me to go and review it. And I like to review it all in one sitting instead of leave and come back and read some more. So either tonight or tomorrow, it depends how tired I am at the end of this. So it'll definitely be reviewed by tomorrow. What I do, though, is I will read through the projects on a first-come, first-served basis. So if you submit it at 7:59 a.m. on Thursday, there'll probably be 10 others submitted, and yours is going to be last to be read, and it takes a long time for me to read through these and give you suggestions. So again, if you're one to wait until the last minute, then you're going to have to expect it to take a little more time for me to review it. And then you'll have less time to submit it on by Sunday. And I recommend not thinking Sunday is a deadline. I recommend Saturday. That way, if something goes wrong, you got a day to deal with it. Okay. If you email me saying you want an extension, I will say no. It is due on Sunday. Okay. And better is a little earlier. You only submit one project per group. In fact, let me share my desktop. Just 1 second. That guy. And I just lost it. There it is. So I want to kind of show you kind of where to find stuff. I've already shown you once, but I want to show you again. I want to emphasize a few things. One, if you go to syllabus, and then project 1. I also have a little cold, but the good news, this is an online class. You cannot catch my cold. It does not go through computers. But you might hear me sneeze a few times. So just let you know, this is the requirements for Project 1. I want to point something out that I strongly recommend you look at before you submit your rough draft. And that is where it says feedback on Project 1 drafts. If you click on that, I showed you once, but I want to doubly remind you. This gives a list of things that I have told people in the past. These were actual feedbacks that I gave on a couple other projects that kind of are representative. So I thought that those would be good ones, a couple of them. You'll notice there's a 1 through 8, and then there's a 1 through 4, and a 1 through 11. So these are lists of things that people have submitted their project draft in the past, and then they needed some adjustments. So I strongly recommend that, the day before you submit it, read through this and make sure you've addressed all of these so you don't get the same suggestion as I'm giving these other people. Does that make sense? Okay, so these are like kind of the top 20 common mistakes type of thing. Okay, and these were, from a while ago, but nothing really changes. Any questions on that? Okay, and I also want to strongly remind you that you do need to submit your spreadsheet, and that could be a snippet of the spreadsheet, the parts that are important, or it could be a link to, if you use Google Sheets, you can share it and then send me a link on that, and that counts. You need to prove that you use a spreadsheet, or I take at least 10% off if you don't use a spreadsheet. So you can't get an A, basically, without the spreadsheet. So that's a big note. You're not allowed to use a calculator is the idea. And in fact, I'll show you the spreadsheet again today because something you may not know, but normally I show you, I say, we're going to do this on the calculator, right? And that's because I'm able to share my screen, but that's a program that I don't have on this screen. I only have it at the college. So I'm going to use a spreadsheet to do all the calculations. So are there any questions about Project 1? Any questions? Let me see if there's any. I'm reading. No questions. Just talk about the president. Okay. So again, I'll be, reading your Project 1 stuff. I'll be looking at the Project 1 discussion forum often, but I do have other classes I teach, so I got to do that. Unlike today, where my class got canceled because our college is closed. But I was outside shoveling snow most of the day, today and yesterday. So, but I think I addressed all the questions at a pretty timely basis, even as I shoveling. There wasn't much going on while I was shoveling. Okay, so why don't I go and talk about the big theorem of the whole course. So this is a very important week, and that is chapter 7. So in chapter 6, we looked at the normal distribution. And what you really didn't get is, why do you care? There's this bell-shaped curve. It's pretty, I guess, maybe, if that's the way you look at beauty. But, why is it important? Why is that something we focus on? There's a lot of distributions, but that's the big one I mentioned. And chapter 7 is going to show you why everything that we ever do needs the normal distribution. So I think I'm going to pop in and do Paint so I can type some things out. Okay, so hopefully you can see that. It's interesting, it's not doing what it usually does. Hopefully you can all see that. If you can't see something, let me know, by the way. Would it be all right if my group just submitted the body of the project for the draft? Like, you don't want to submit your introduction and conclusion? Well, because that's usually just a paragraph or so each. Maybe I'm not following you. I mean, you could submit whatever you want and I'll read it. One thing, you only get one submission for your draft. I only give you feedback on a submission once. So the problem of submitting parts of it is that you only get to submit one part and then it's over. Then you have to hope that you did the rest right. Does that make sense, Will? But again, if you can't get it done by 8 o'clock on Thursday, then you can't. Then you need to submit what you got is the best. Yeah, so what I do, so you're most concerned with the data analysis. The whole paper is the data analysis and the suggestions based on the data analysis, but the body has both. So if you don't have suggestions based on the data analysis, then you don't have a paper. Throughout the entire paper, you got to have your suggestion, not just a bunch of this is the mean, this is the standard deviation. And then after you respond, yeah, so I will keep reading. So I'll only ask questions, though. I will only ask questions using the Project 1 discussion forum, unless they're very personal. So, for example, if you're killing your partner, you know, and you're really not getting along, that's probably something you don't want to post on your discussion forum. But any question about the project itself, that has to be popped into the discussion forum. And the idea is all of you should read that so you can hear the feedback, hear what works and what doesn't work. So look through that project discussion forum, and that will help you also in getting a good project written. Does that make sense, Will and Tammy? Okay. Okay. Can you all see the paint? I just wanted to make sure because it's not doing a green thing around. Okay, you can. Okay. Again, I'm not used to this technology at home. I usually do the webinars at the college, and things look different. So I'll keep the chat up here. Usually I have the chat on a separate window. I don't even have a separate window, but I'll do my best. Okay, so here comes the big theorem of the entire class. And we haven't had any theorems in the class. This is the biggie. Or I guess we've had a couple little ones. You know, we've had Chevyshev's theorem, that's in the book, and should be in your project possibly, or the empirical rule. But this is the big theorem, and it is the following. So let me go. I've got to move things around so I can get to them. There we go. Text. Doesn't need to be 48, that's for sure. How about 26? Let's see if that'll look good. I'm going to do it in red. And this is called the central limit theorem. What it says is the following. Okay, so, and hopefully you know this class is really all about sampling. It's all about collecting data and then looking at data and analyzing it. And what we want to do is we want to say, well, when you collect data, what is the distribution of the data that you collect? Now, it's a little different to say what's the distribution of the data you collect, but let's suppose that instead of the data you collect, let's suppose that you're in the job of collecting data, and you collect data over and over and over again. So you're going to be conducting surveys all your life for eternity, basically. I know for some people that's hell, but we're going to do it anyway, okay, at least in theory. So we're going to look at all possible surveys that can be conducted. And let's fix a sample size. So let's suppose you have a sample size of n. That n, we'll see there's a big difference between n being 30 or less and n being greater than 30, and that'll be in the central limit theorem also. But either way, the first part will work for whatever we choose. We want to look at all possible samples that you could collect from a population. And what we want to do is we want to say, well, each sample that you collect will have a mean. Does that make sense? So each sample will have a mean. There it is. So each sample will have a mean, and we can think about each of those means that you get from all possible samples and look at the means itself. themselves as the data values. And if we look at all the different means that you could get from sampling with a certain sample size, then that is going to be special. So let me write that out. First thing, we call the distribution of all possible means a sampling distribution. And what the central limit theorem says is that if you consider all possible samples of a fixed sample size from a population, then we can consider the distribution of the means of these samples. Okay, hopefully that makes sense. We want to say, well, if you have a whole bunch of means and we want to look at the distribution, then there's some main things you want to ask about the distribution. One is, if you have all these different means, what is the average of all the means? Okay, so the first thing it says is that the mean of all possible means is the population mean. So if you, let's say you conducted a study of Americans, of let's say 100 randomly selected Americans, and you wanted to find out how old they are. And you look at all groups of 100 Americans. So every group of 100 Americans will have an average age. Okay, there's going to be a whole lot of groups of 100 Americans, by the way, more than you could ever actually do, but you can imagine it at least. So if you take the mean of all of those mean ages of samples of size 100, that will be the population mean. When you have this situation, when the mean of all possible statistics is the population statistic, then we call that an unbiased estimate. If it's not, then we call it a biased estimate. So this says that the mean is an unbiased estimate. Any questions on that? Okay, then we have the following. So, mean, what's the next most important of all statistics? The standard deviation. So what we want to do is say, well, if we look at all the standard deviations, each of these samples of, say, 100 Americans will have a standard deviation. Well, what do you think the average of all of those standard deviations will be? Yes? So what do you think the average of all of them are? Okay, it turns out that the average of all possible standard deviations is not going to be the standard deviation. It's actually going to be the standard deviation, or the population standard deviation, well, divided by the square root of the sample size. And we call this the standard error. The standard error will be the standard deviation of all possible, or the mean of all possible standard deviations you can get from that sample size. Okay, and that's called a standard error. What it does is it tells you how good an estimate your mean is, because that's what the standard deviation is. It tells you how far the data values, on average, tend to stray from the mean. And what this says is that the sample mean does not stray as far from the population mean when the sample size is large. Because if you have a large number in the denominator, you get a small number when you do the arithmetic. So again, let me ask you, are there any questions about this big theorem? There is going to be a next part also. Any questions? Okay, so let me do the next part. It's the part that I promised. Furthermore, the sampling distribution so what you want to do is you want to say, okay, you have you know the mean, you know the standard deviation. Well, what's the shape of the distribution of all possible means? That's called the sampling distribution, shape. And this was the promise I gave earlier, is approximately normal. As long as n is greater than 30. Where have you seen n greater than 30 before? This is something you should all know because it's coming up. Or it came up recently for y'all. Where have you seen n greater than 30? Yeah, the project. Okay, so the project. Okay, so the reason why I'm enforcing that you have to have a sample size greater than 30 is so that you have good data. And good data means you know the distribution of the sampling distribution. So you know the shape of the sampling distribution. That's not the same as the shape of the sample. It's not the shape of the population. It's the shape of the distribution of all possible means with the sample size that you did. Any questions? I'll have some examples. I know this is pretty abstract, but the examples might help. I'll have some very useful ones. In fact, I'll have one where part of that helped me actually literally make over $100,000. Okay, a few $100,000, which isn't bad. Maybe you can also. Okay, or at least understand it. So any questions about the big theorem of the entire quarter called the central limit theorem? Let me say it again. That's how important it is. So if you consider all possible samples of a fixed size, so you think of yourself as being in the business of collecting samples, and you look at all possible samples, then you take the mean of each of those samples, and what you can say is that the mean of each of those samples, the mean of the means, is the population mean. But if you look at the mean of each of those samples, there's a whole lot of different means, and you take a standard deviation of that collection of means, then it won't be the standard deviation of the population. It'll be the standard deviation of the population divided by the square root of the sample size. And if you look at all the different possible means from all possible surveys of a sample that has a fixed sample size bigger than 30, then the distribution will always be approximately normal. And the good thing about being approximately normal is that means that your calculator or computer can easily come up with the solution. Okay, come up with probabilities. Whereas if you don't know the distribution, which is the case in pretty much everything else you ever do, then you can't compute anything. So this allows us to make computations as long as your sample size is larger than 30. And what you're computing is you're computing your best guess for the mean. You're computing how far you think the population mean might be from the mean that you got in your sample. That's what you're computing. So we're able to make some calculations as long as your sample size is greater than 30 because of this normal distribution. So let me give you an example. And again, this is my favorite example because again, I have made more money than a lot of you would ever think you can make, but I have. And that is, let me share, and I'll show you how to do it. Okay, it's not easy, by the way. Okay, so anyone recognize what I'm looking at right now? Yeah, this is the stock market. And what I want to look at is I want to analyze what is a good investment. Okay, I know maybe none of you really care about making money. Maybe you're all billionaires, although billionaires usually care more about making money than people who aren't that rich. But very rich people, you know, they got rich for one reason or another, and a lot of times it's for doing this right, and that is investing. Okay, so one of the things you want to say is what is the difference between, say, investing in a stock, and a stock might be Apple. Apple was big in the news today. Anyone know what the big thing about Apple was today? Anyone read the news? Apple is back in the world's largest company in terms of net value. Okay, so you might want to invest in Apple stock. Sound good? Okay, it might be good, but when you invest in stock, are you always going to make money? Yeah, definitely not always going to make money. Okay, if I tell you the mean change, Apple's an expensive stock, but again, you can just, you don't have, if you have $1,000, you don't have to buy, you know, a fixed number of shares, you just spend $1,000 worth. Does that make sense? Yeah, so it doesn't matter how expensive the stock is. What matters is whether you think the stock's going to go up or not. Okay, but let's suppose that you really don't understand the market much and you just invest in a stock blindly. So the mean percent increase in stock over the last, I don't know, 20 years or so has been around 8%, 8 or 9%. Let's call it 8%. Okay, but the problem is, does that mean that you will, if you invest in Apple, you're going to be making 8% at the end of the year? No, what's the problem? And think about statistics, that's the hint. Okay, there's error, but what do we call it in statistics? Standard deviation, yeah. There's a big standard deviation for individual stocks. So if you buy one, you know, a few shares of Apple, I don't know what it's at right now, but you could figure it out if you wanted. You bought a few shares of Apple, yeah, on average you might make 8% because that's what stock tends to do. But the problem is that there's risk, and the risk is based on the big standard deviation. Does that make sense? So let's suppose, I'm making this up because I haven't done the research on Apple. Let's suppose that you researched Apple and you found out that over a 5-year period, the standard deviation is 20%. So the first question is, let's assume that it's also a normal distribution, just to make life easier for us. So the big question is, what's the probability of losing money? Of ending up with losing, because losing is awful, right? Kind of makes you feel pretty bad. Okay, so again, we have an 8% average. And what did I tell you the standard deviation was? 20%. Okay, and by the way, we'll call percent to units so you don't have to move decimals. You can get away with it as long as you're consistent throughout. So let me go ahead and let's go to my Google Sheets. Again, I can't get to the calculator program because that's at work. And let's do a computation. Okay, so let's do the computation. We're going to have a normal distribution. Mu was 8. Standard deviation we said was 20. And we want to find out the probability of losing money. Okay, if you want the probability of losing money, that means we're on the negative values. So the lower bound is going to be negative 99999. That will definitely make you lose money. Upper bound is 0. Right? Anything over 0, you didn't lose money. Okay? Anything under 0, you lost money. Okay, and if there's any questions, please let me know. Okay, and then we hit enter. And this says that the probability of losing money is about 34%. So let's suppose that this was, savings that you had, so to make sure that you could actually afford college. Would you be okay with a 34% chance that you're going to lose money and not be able to afford college? Would you be all right with that? Okay. Okay, probably not. Okay, so here's another thing you could do. You could put it in the bank. What is the percent interest in the bank? If you put money in the bank? Okay. You get like a 0.5% interest. Okay. Which is low. But what's the standard deviation if you put money in the bank? It's not 1. It's 0. It's 0. Banks are FDIC insured, right? As long as we're going to assume that America doesn't get destroyed in the next year. And I think we could assume that. I think that's fair because we got bigger issues than not going to college if America gets destroyed. So the standard deviation is 0. Does that make sense? So in terms of risk, standard deviation wise, the bank is a better bet if 34% is not something you can handle. Does that make sense? Okay, so now let's do something different. Let me go back to the stock market. Have any of you heard of something called an index fund? Any of you heard of an index fund? Okay, some of you have, and I don't know if you know what it is and why you want it, but let's look at I like this one because it's got a number, S&P 500. Do you know anyone know what that is? Yeah, Standard & Poor, what it means is that there are 500 stocks that are included in the S&P 500. Now, we're going to assume, which is not a great assumption, but if you do it for 5 years, it's not too bad, that they are independently moving. So in other words, if one goes up, that doesn't tell you what the other one's going to do. Okay, which isn't the best assumption. You could do better, but it's a little complicated to talk about how to get a more independent solution. But the word for it in investing is called diversification. You've probably heard of that before. And you've probably heard that diversifying is a really good idea. So we're going to assume that we're going to diversify stock. And S&P 500, as you might guess, has 500 stocks. So we're going to assume that it's diversified, which means they're independent of each other. So now we could ask the same question, what's the probability of losing money? So if we want the probability of losing money, we first have to compute the standard deviation. The mean of all possible sample means of 500 stocks is still going to be 8%, because that's the first piece of the central limit theorem. The standard deviation, on the other hand, changes significantly. That is going to be 20 divided by the square root of 500. And what you get is about 0.9. Any questions on that? So now we could say that our new sigma is 0.9. And if you look at the probability of losing money with a fully diversified investment of 500 is 0. And you're averaging 8%. Okay, now again, I want to give you a warning. S&P 500 is not fully diversified. But if you can fully diversify, if you can study the market, really understand diversifications, that means you're going to do international, you can do real estate, you can do gold, you can do all kinds of different investments, then you could reduce your risk significantly. So let's suppose you can find maybe 10 different things. 10 different things to invest in that all have an 8% average. Then we're talking about square root of 10. If you do that, that's 6.32. We've dropped even with just 10 investment, we've dropped our risk from, what I say, 34% to just 10%. Huge difference. It's a huge difference in the standard deviation and the risk, the probability of losing money, if you have a diversified investment. Okay. Of course, one of the hard parts is to understand what diversified means. You know, that you're not going to get in my class. That you really have to take an economics class to understand what a diversified investment is. Okay, and you can do a whole lot more than that. I'm not going to get into it with math and economics and make serious money. So trust me, I've done that. Okay, it's bought me a few houses. Okay, any questions on the power of the central limit theorem? Any questions on that? Okay, so notice this is a central limit theorem for means. The question was quantitative, right? The question is what percent did the stock go up at the end of 5 years? Is that clear? Now, what happens if instead of quantitative, you have a yes or no question? Any questions on the question? So let me give you an example. And the good news, I haven't even researched this. I was too busy shoveling snow, but I know it's always there. Let me go to Gallup. Is it UP? Yeah, it's UP. Let me get there. And I always have to move this thing. Whoops, I didn't mean to do that. There we go. Let's go to news, which is, I think, at the bottom. There it is. Maybe they'll have something about my competition tonight, which is Trump. Let's see. Okay, solid majority still opposes new construction wall and border. Okay, do we really think that's true? So if you click on it, and what they did is they did a survey, and we had 60% opposed significant new construction. here's the question I have for you. Okay, and you can chime in. Does that mean that 60% of all Americans oppose significant new construction on border walls? It doesn't. What does it mean? What does that mean? Yeah, just the ones that ask. So here's a deeper question. The article was a majority oppose it. Now, do y'all know what a majority means? This is important because I've already seen one mistake on the projects. Actually, it's not quite 51%. It's over 50%. 50.5% is just fine. Does that make sense, Tammy? Yeah, so over 50%. Notice, by the way, that's not the same thing as the mode. The mode is not always a majority. So, for example, the highest bar in the histogram is not always a majority. It might be only 25% of the answers. Okay, I'm mentioning that not in the context of central limit theorem, mentioning that for the project so you don't make that mistake. Okay, so majority means over 50%. So what is the probability that if only 50% opposed the new construction on border walls, and we did another study of, let's find out. You go to the nice thing is you go to the bottom, you can always find out. Where was it? Survey methods. Here we go. They did 1,017. So let's write this out. So we have 1017 was our sample size. We had 20%. We had 60%. Sorry. Was what we call our p hat, which is a sample proportion, 0.6. I don't know if I've mentioned it before, but P is for proportion for the population. We don't use the Greek letter for that like we do for the mean. And the reason for that is, anyone know what the Greek letter is for P? Anyone know? It's pi. And that confuses everyone if I call it pi. So we use P with a little hat on it. So that's going to be our sample proportion is 0.6. And in particular, 0.6 is our sample proportion of yes voters. Okay. And then 0.4, which I'll call Q hat, was our proportion of no's, 0.4. But we have P was 0.5 is this assumption. How unlikely is it that we had exactly 50% or less, basically, is what we want to look at. So in other words, if it was 50%, what's the probability that we'd end up having 60% or more oppose the border wall? Any questions so far? All right, so now we need some pieces of the central limit theorem that I haven't discussed yet that have to do with proportions. So let me write this out, and I need to, let's see if I got everything I need. Yeah. So let's go back to Zoom. Back to Paint. Let's go select. Oh, it just did it. Good. Okay. So new central limit theorem. This is called the central limit theorem for proportions. I'm not going to write everything out because it takes a long time to write, but I'm going to write a little bit. Text. There we go. Make it a little bit smaller. So this is called the central limit theorem for proportions. And it's kind of a similar idea. We want to say, well, we're going to think about surveys that you could do. In this case, it was sample size 1,017. the letter we use that for is n. So if you do a sample size n, so we want to look at the sampling distribution for proportions of sample size n. So let's write this out. The sampling distribution for proportions of sample size n with probability of success P is, I guess, has mean and this one's a little, sorry, that has mean P. So in other words, the good news is if you take all the possible samples, you can have a sample size n, and you look at the proportion of yeses for all sample sizes, for all samples, and you take the average of those proportions, you're going to get the population proportion. That's a good thing. That says that the sample proportion is an unbiased estimator for the population proportion. So it has mean P and standard deviation. And this one, oh, shoot, it just died on me. Sorry about that. All right. I have to rewrite it. Sorry about that. Again, I'm not used to using this computer with Zoom and everything else. So one more try. Can't hurt to hear it twice. So the sampling distribution with sample size n and portion of success P has mean P and standard deviation Let's see if this works. That worked. Good. I won't make the same mistake twice. I need to go to brush because I need a square root. So the first thing is a standard deviation. I'm going to put P with a little hat on top. That's sigma sub P hat. And that's equal to the square root of P times 1 minus P over N. But we need the sample size to be large enough to make it normal. Okay, just like the central limit theorem we had before. So the sampling distribution is approximately normal if NP is greater than 5 and N times 1 minus P is also greater than 5. This is what our book uses. Some book use 10, by the way. Usually want large sample sizes is the idea. So, but if you have large enough sample sizes, this works. Any questions on this idea? By the way, n times p, do you know what that is in like simple words? Do you know what n times p is in simple words? I know it's a strange looking formula, but it's actually pretty simple. You thought? Let's say n was 200 and p was 60% or 0.6. What's n times p? What does it represent? Any thoughts? Okay. So if you take the sample size and you multiply by the percentage of the people who said yes, that gives you the total number of people who said yes. Does that make sense? And 1 minus p, if 60% said yes, then 1 minus p is 40%, and that's the percent that said no. So n times 1 minus p are the number of people who say no. Any questions on that? Any questions? Okay, so now we're ready to compute and do our example. Our example, we're saying, well, let's suppose that we really didn't have a majority. We only had 50%. So let's suppose that p was 0.5. N again was 1,017. So if I go ahead, we could say for our example, sigma sub p hat is equal to the square root of 0.5 times 1 minus 0.5 divided by 1,017. Any questions on that? Any questions? Okay, so now I can start doing some computations. I got to reshare. So let me go to reshare. Let's go back to the internet. And let's do that little computation. And that was square root of 0. Let's put it fancy again. That's fine. 0.5 times 1 minus 0.5. 1 minus 0.5 is still 0.5 in this case. Divided by 1017. And we get 0.0157. Okay. Any questions so far? So that's doing that information, and that is going to be the standard deviation of the sampling distribution. Kind of tells you how likely the estimate is going to be close to the population proportion. So notice that I don't even need a calculator for this. This is 1.57%. And we're assuming, again, we're saying if 50% of the population, so let me go back to the article. So this one, I can't see it. Yeah. So we're saying that if 50% of the population, if it was just 50%, supported the border wall, and if we did a study of 1,017 people, then what's the probability we're going to get at least 60% against the border wall? Does that make sense? So notice the standard deviation is less than 2%. Okay, 60% is 10% more than 50%. So we're talking about more than 5 standard deviations away. Now, hopefully, you don't even need a calculator, I hope. What do you think? How likely is it that randomly you're going to end up getting more than 5 standard deviations away from the mean? What do you think? With the normal distribution, without even using a calculator. So the z-score being more than 5 is another way of saying it. Any thoughts? I'm looking in the chat in case you have some, hopefully you have ideas. What do you think the chance might be of being farther than 5 standard deviations from the mean? Above the mean in this case. Yeah, even worse and not likely. Remember, 3 standard deviations is an extreme outlier. Do you remember that? 5 standard deviations is virtually impossible. Is that clear? So what we can say is that because the probability of getting 60% to say they're against the wall, if we only had 50% of America against the wall, and given, of course, this is a random study, no bias. Bias kills everything, by the way. So given that this is a random study with no bias, that tells you that probability is so minuscule, a big red flag gets popped up. Do you guys agree? Right? If you have 1 in a billion chance of something happening, and then it happens, you say, well, maybe something was wrong in the calculation. And what's wrong in the calculation is saying, well, only 50% are against the border wall. So what we're going to be able to say is that, aha, there must be more than 50%. That assumption of 50% couldn't be right. It's too unlikely. Any questions at all on this idea? And I want to let you know this is what the class is all about. It's all about being able to either look at someone else's data, collect your own data, whatever it might be, and then use the central limit theorem and other theorems that we're going to have, okay, adjustments to the central limit theorem, to see what you can conclude, whether the assumption of not having majority could really happen. In this case, we say no. It's so unlikely. It's pretty good to bet on the fact that no, we have a majority. Any questions at all on the idea of why we care about the central limit theorem? We can't do this without the central limit theorem. Notice we needed to do these calculations to find out what the standard deviation is. If you didn't have the central limit theorem, basically you give up. And in fact, if you have NP or NQ not bigger than 5, your sample size is too small. You can't do anything. So that means that you need a bigger sample size. But in this case, N is 1,017. Our P was 50% of that. And that's certainly bigger than 5. It's over 500. So this is a sample that's definitely large enough. And in fact, Gallup will always have it as goal over 1,000. And that we talk about next week, why 1,000 is even a better goal. It's not so you could be ridiculously bigger than NP and NQ, but greater than 5. There's a different reason. Okay, and that's going to have to do with this next line, but that's next week's stuff. So are there any questions at all about applying the central limit theorem, either for a mean or a proportion? Okay, I want to go back to the central limit theorem, and I want to remind you again, if instead of proportions we had means, I want to give you the, I want to go brush. I want to do it in red. If we had sigma sub x bar, x bar, as you've seen in your calculator, represents the sample mean. So the standard deviation of all possible sample means, that's the first example. Remember, was the square root, it was mu, the population mean, divided by the square root of n. So I want to give you the formula because it's that important. So one of the things that tells us is that if we want to reduce the standard deviation, which means we want to make sure our study is better, okay? It's a better prediction of, oh, sorry, it's not mu, it's sigma. That's better. It's sigma over root n. So if we want it to be a better prediction of the sample mean, of the population mean, using our sample mean, then we want a larger n. And notice that n is in the denominator in both of these, whether it's sigma sub b hat or sigma sub x bar. So there's a root n in the denominator no matter what you do. So that tells you, for example, if you survey 100 people, that's 10 times better than surveying 1, because the square root of 100 is 10. If you survey 9 people, then you reduce the standard deviation by a factor of 3. Any questions on that idea? If instead of means, if we want totals, if I told you that we had a sample of size 200, okay, so I told you we have a sample of size 200, let's say a bunch of customers at a restaurant. And on average, they spent, let's say, $10 each. How much money did you, if you own the restaurant, how much money did you bring in that night? So again, if you had 200 people, and on average, they spent $10 each, how much money did you bring in? This isn't supposed to be a very hard question. What can you tell me? Yeah, that'd be 2,000. So notice that if you want the total, so now let's go to text because it's easier. One more time. I click that. So the total, new mean for the total, is going to be equal to the mu. Let's go back to brush. Probably should have done brush anyway. Times n. Any questions on that? And if we want the standard deviation, sigma for the total, we usually use a summation sign because we're adding them up. And sometimes you do sigma x. We're adding all the x's up. Well, that's going to be sigma sub x bar times n. Now see if you can remember, what is n divided by the square root of n? Got to bring back your algebra. What's n divided by the square root of n? See if anyone can tell me. How do you simplify n divided by the square root of n? I'll write the sigma part first. All right, I don't see you all jumping in at once. If you take n and divide by square root of n, not quite a half. Not seeing it, it's root n. And that's a central limit theorem for the total. So one way of looking at it is n to the 1 divided by n to the 1/2 is n to the 1 minus a half, which is n to the 1 minus a half is a half. So that's n to the 1/2, which is root n. That's the algebra proof of that. Any questions on the totals? So for the totals, we have a new formula. It's a lot of formulas. But as I mentioned, you always get a note card if you want. So you can put these on note cards for the midterm and the final. Any questions at all on the central limit theorem for proportions, for means, or for totals? Any questions? Okay, what I need to do now, because it's already past 7, and I do what I can on that one. Let's, there we go. I need to give you a secret word. Ah, shoot, one more try. Gotta click that first. And the secret word for today is error. And that's because, again, remember, we call this sigma sub p hat or sigma sub x bar or sigma sub summation of x. We call that the standard error. So error is really important. And what we find out is that if n is larger, then we reduce that error, which means that your sample mean or proportion or sample total is going to be more likely to be close to the population mean, proportion, or total. And that means you can have less error in using your sample to estimate the population. So let me stop the share. And hopefully I didn't confuse all of you too much. Again, there's the book and the long video. Central limit theorem is pretty deep. It's probably maybe the most confusing topic of the class. But hopefully you'll get to it and you'll figure it out. So are there any questions? Maybe I'll jump to paint one more time. I want to show you something. Just some notation. So let me, I want to summarize all this stuff in one shot, in a few shots. So what we can say is you could have, say, x. Yeah, this is one of the more confusing. Tilde and mu sigma. I typed it out because it's easier to type than to write. The central limit theorem says that if we want to look at the sample mean instead of the individual, we get something different. And I think I do need to do brushes, too many symbols. And what that says is that x bar tilde n still going to have mu, because that was the formula. That was the central limit theorem first part. But the standard deviation changes. It's going to be sigma divided by the square root of n. And that's if n needs to be greater than 30. And we can say that the summation of x is normally distributed with mean mu times n. And standard deviation sigma times the square root of n. And we can say that p hat is normally distributed with mean p and standard deviation square root of p times 1 minus p the square root needs to be longer over n. So those are the three big formulas. Okay, so P stands for the population proportion. N stands for the sample size. So on the Gallup one, our N was 1,017. Our assumption was that P was 0.5. Does that make sense, Chanel? Okay, other questions about this? Okay, and by the way, for the third one to be true, the first two you need n greater than 30. For the third one, you need n times p greater than 5. And n times 1 minus p, which sometimes you call q. So I'm going to write q, it's easier to write, is also greater than 5. Q is 1 minus p. So q is the proportion of no answers. So that's the sample size issue there. So again, this is the central limit theorem. If I ask you to state the distribution, I want you to write these symbols, and of course you're going to have numbers to plug in. I don't even want to say if, when I ask you on the midterm. So hopefully you'll remember to use these formulas, if appropriate, when I ask you to state the distribution. You'll remember to divide by root n, or multiply by root n, or do the p times 1 minus p divided by n in a square root. I'd say about half the class forgets, and I take a lot of points off, so don't forget, because that's kind of the whole point. Any other questions? And again, I'm always happy to answer questions. If not, we can call it good night. It's 7:13, which is about what I like to do. Hour and 15 minutes or so is kind of an average. So are there any other questions about anything? Yeah, there's a lot of word problems. There's, you know, that has a lot more. You could hit pause and all that. And I gave you a few more. The book has them also. So there's lots of ways, whether you do the PowerPoint or the hour-long video, which is a PowerPoint, or you read the book, it's the same. Same notation, same different examples, but same idea. Okay, any other questions? So Tammy, if you're lost, definitely.
I'm here.
Courses. Yeah, question?
Well, I was waiting to make sure if everybody was done with this, because I have a question from last week. So I wanted to get through this first. So
and what's your question from last week?
So from last week's homework, we did the discussion question where we did the weight of a coyote and all these different options that we had. And when I was looking online, I could find problems that obviously I could look up the number of days the average woman is pregnant. But I was having a hard time finding standard deviation. And in your instructions, it said, if you can't find standard deviation, then just do this. That's where I got totally lost. If you don't know what the standard deviation is, if you're not given that, then how do you find that for the example, or how does that develop?
Okay, you got to kind of estimate it. And you're asking, how do you estimate it, right?
So it's just a guess, or how do you estimate it?
It's a guess, but not a blind guess.
Okay.
It's an educated guess. So let's suppose we wanted to find the standard deviation of women's heights.
Okay.
Okay, first thing, I'm going to tell you the average woman is 64 inches tall.
Okay.
Okay, I have looked that up. It's been a few years, but I don't think anything changes. Okay, so we know that the mean is 64. And if you don't want to do it in your head, that's 5'4".
Yeah.
So now, think about women that you know. And if you think about, like, most of the women, 95% of the women or so, if someone is going to be in that really unusual time, in that thing, how short or how tall do you think they might be? How many inches below or above 64 inches or 5'4" do you think they might be to like turn your head and say, wow, that's short, or wow, that's tall?
Like 6. If somebody had a 6-inch different, a 4 to 6 inch different, like 5'8", that wouldn't be that big. But if they were 5'6", I mean, or 5'8", whatever, you know.
Okay, so I'm going to go by 6.
Okay.
So that's 58 to 70.
Okay.
Right? I subtracted and added 6.
Right.
Got it?
Yeah.
Okay. And in particular, you could just go by 6, actually. If it's real unusual, it's an outlier. And by our definition, an outlier is 2 standard deviations from the mean, right?
Right.
So 2 sigma. I'm going to go approximately, because we're just guessing the 6, right?
Yes.
Is 6. So what's sigma?
3.
Uh-huh. So if you were going to get a good educated guess on the standard deviation, you would say 3 inches.
I understand.
Does that make sense?
Yes.
And again, that's an educated guess. If you just threw out a number like 74 for the standard deviation, it's ridiculous. It's a guess.
Right. Right.
Do you see that?
Yes, I do.
Yeah. So you want to think about what makes an unusual event, and we're defining unusual means that there's a 5% chance of being that far away from the event or farther.
Sure. That makes sense. Thank you. I was having a terrible time trying to get this across in email, so I appreciate your patience.
Yeah, and good thing I'm on Paint, which means we can actually see it, and can do it as we go. Any other questions? Okay, we still have Chanel and Ozzy. Any questions? Okay, not yet, Chanel. So if you do have questions, you can always post and I'll answer. Yeah, again, when you read through the chapter, watch the long video, it should get easier and easier, and then post questions when you're still stuck on doing some example problems. Because chapter 7 is confusing. All right, good night. And last chance. Okay, thank you. It looks like we can call it a night. So for all of you who are watching this as an archive webinar, don't forget, somewhere in there is a secret word. You need to post a secret word quiz by Sunday. And please keep in touch about your project. I'm here to help you out. But if you don't send me your draft and post questions, I won't be able to answer them. So I hope it goes well. I'll be here for you in and out of the internet. And have a great week. So have a good night.